Hi folks, this video is going to be very short, and I'm not kidding on that one. I'll spend more time on the simulation than anything here. We have obviously been dealing with mass spring oscillations for the last 2 weeks now, so we're going to move out of that for another couple of class periods and talk about pendulums. I know you guys love bringing back the pendulums, but this is actually very easy to understand and solve for. So when we're talking about mass spring oscillations, remember, or specifically simple harmonic motion. Simple harmonic motion is a result of a restoring force that is conservative that will always bring the object back to equilibrium. Okay, so we have a couple of different restoring forces, though, that are conservative. We've been dealing with ideal springs, but now we're going to be talking about pendulums, so obviously the conservative force is gravity that's going to maintain the pendulum motion swinging back and forth. Very similar to, and this is the only equation we're going to have to deal with, very similar to a mass spring system, pendulum oscillations can also be timed using the equation T equals 2 pi times square root of L over G. So notice that the mass of the pendulum doesn't matter, which we should understand that by now. But the only two factors that are affecting how long it takes for a pendulum to swing through one complete oscillation is simply the length and gravitation. Now, there are a couple of assumptions that we're making here. First of all, we're making the assumption that all of the mass is located at a point and the string has zero mass or negligible mass. If you think back to all of our fun rotation unit, moments of inertia for different objects, we would have to factor that in, okay? So we're dealing with a single point mass for a pendulum. If we had what's called a physical pendulum, where it's just a rod that's rotating about the axis, swinging back and forth, the period equation is going to look a little bit different for that. So once again, all the mass is located at the point. The string is negligible mass. Also, the equation that's given above is actually just an approximation. So in order for us to be able to utilize that equation, we need to keep our angle very small. And when I say 5 degrees or less, we actually want the angle to be next to nothing, just to have a really small oscillation. So when we do our pendulum lab here in another couple of days, we want to make sure that we use even a 1 degree angle when we're pulling this back. Okay, so I'm going to, pretty much the notes, I'm going to show you just a couple of things real quick and then be done. I'm going to make myself go away here. First of all, this is the actual equation for a pendulum. Okay, and I don't think we want to be able to use this. So notice that T equals 2 pi times square root of L over G. As the angle becomes larger, these additional expressions in this equation become more and more significant. Okay, but with a very small angle, these expressions are insignificant, so we're just multiplying this by 1. Okay, so this is what I'm talking about with this. Okay, so I'm going to insert a timer here. If I just pull this pendulum back 1 degree and let it release, and I hit play, we get a period for the pendulum of 1.6784 seconds. Okay, we could go through the math on this real quick and use the period equation to verify this. It has a length of 0.7, and we're obviously using gravity, so we could verify this time. But if we use a large angle and we release this, the period now jumps up to 1.7766. Once again, now that angle is significant, so we would have to factor in more parts of that expression in order to solve for it. So long story short here, we simply just want to keep the angle very small in order for the period equation to work. Okay, that's it on the notes. That's it for this part of it. So after we get done with all of this, we will take a quiz over where we're at. So anyway, I'm going to end this video. Mr. McDonald's going to do a couple of practice problems for you guys, and that is it.